To speak here today. My name is Igor Katenka. Here I represent what they usually call the academia. Well, in fact, I'm referring to the Russian Academy of Sciences, and in particular SPIRAN, which is St. Petersburg Institute of Computer Science and Automation. I'm head of computer security department there. I've been with this particular university for about 10 years. Before that, I worked for the Ministry of Defense. And for the last 20 or 30 years, I've been involved with issues of security. Speakers usually crack jokes to establish a rapport with the audience. I'm not very good at it. What I've got here is a pretty boring presentation, or at least a pretty scientific one. I've been given 45 or 50 minutes, and this time is certainly not enough to explore very deeply a subject that large. I can either focus very narrowly on something specific, or I can give you a superficial treatment. Actually, my report, for some reason, has been classified as 300. However, I removed all the formula from my presentation to make your life easier. It's going to be mostly verbal, pictures as well, which means I've simplified it somewhat. But for those who would like to get a better understanding of the subject, I will be available later for a discussion, or you can come and visit our institutes, and we shall be happy to consult you if need be. So my presentation is going to focus on attack modeling, both analytical and dynamic, identification of vulnerabilities, and methodology, scientific, if you like, methodology that supports all that. Well, I'm also going to be talking about intervention and prevention. Fighting penetration. I'm going to be talking about SIEM systems today. I will provide you with a definition as we go on. We often say that most of the research, because of most of the money is concentrated in Moscow, most of the research is also carried out in Moscow. However, St. Petersburg sits pretty close to the border, and we run a number of international projects. Usually it is an international project that you do something interesting, something on the white side, as we often say in conferences like this. On the other hand, these projects help you build your team, finding and retaining some talented youngsters. So this report essentially is trying to describe the current status quo within FP7. Well, the European community has been sponsoring major projects like this. So you certainly know that usually in projects like this, or in programs like this, up to 12 countries can collaborate. There are lots of SIEM systems around, some large corporations develop and promote them. So you might start wondering, what is the potential contribution of the academic community to a collaboration like this? That I will also try to broach in my presentation. I'm sorry if my presentation might sound superficial from time to time. Unfortunately, we don't have enough time to provide a deeper treatment of the subject. Certainly, we won't have enough time to discuss all the components of SIEM systems because, in my opinion, correlation mechanisms are the most important one, because you need to collect a multitude of different events, analyze them, and get a well-correlated, non-conflicting, consistent sequence of events. So we shall be talking about modeling, security metric or security indicator computation, and visualization, which means that we assume for the beginning of my presentation that we have already collected the information required. What do we do next? How do we support the work of an administrator or a user of an SIEM system in terms of managing information security? I would like to point out I would like to focus on three elements in my presentation. First, I will tell you very briefly about SIEM systems, by way of introduction for those who are not directly exposed to that. Then I will tell you about the Massive project, and then we shall talk exclusively about analytic modeling, security analysis, and visualization. I will remain sort of conceptual, but will deep into details from time to time. Well, the terminology is quite a mouthful, really. Russians don't like the full name, Security Information and Event Management System. That's why in Russia we have developed a number of other monikers for it. Whatever you call it, obviously, a SIEM system is designed to extract information about the events happening currently, monitor these events, analyze them, and then proactively manage security incidents, which means that it should support decision-making. It should support us also in performing countermeasures. So we have, for example, a static situation when we have some vulnerabilities, for example. On the other hand, you have some dynamic information because you have users working in the same system, and the system is attacked by attackers, essentially. That's why it has to have a proactive component, which means that it has to support your measures before the situation becomes critical. And it is critical not when the system goes down, but even when an attacker gets access to some confidential, classified data. So the information available to us in a system like this is configuration data, application data, hardware data, event data, system logs. So by using all this information, you should be able to monitor the situation and take countermeasures. Traditionally, SIEM systems have collected logs, analyzed logs, processed them, and supported decision-making on the basis of this information. Well, you'll see here that we've updated this definition to include attack identification via, for example, signature testing or anomaly identification. So you should also assess the level of security, again, on a static level and otherwise. So, for example, user has installed a new application, it has vulnerabilities, and then the system should be notified of these vulnerabilities. Again, it should support risk management because we are limited in resources, in our capabilities, including organizational ones. If it's a large and distributed system, then you would want to make sure that all elements of the system are up to date. And risk analysis would certainly be a very important function, and again we should deal here with a prioritized list of risks, because after all we live in a world of limited resources. Well, next you would like to investigate all incidents, or at least all the material ones. So both modern and future SIEM systems should accumulate this information for future decision making. It should also identify deviations of critically important resources and business processes from internal security policies. Security is a support function, and the first thing it should support is day-to-day business processes. So whatever we do, we need to make sure we are not undermining the reliable performance of corporate business processes. There is this notion that security should not require more than 20% of your resources. I think we're talking about system resources here, not corporate resources. And this is obviously an important function of a future SIEM system. So we can be tracking the current situation, and then we can scale up or scale down our defenses depending on the situation. And it should also support reporting, which should be a typical function, really. I'll show here are different sources of information, and you see that we extract data, we manage data, analyze data, and then we deliver the data via documents or via online alerts or correlations. This is obviously the most important classical triangle for any monitoring system. We have lots of data below and a smaller amount of compressed correlated data at the very top, which will be required to make educated decisions. And shown on the right are essentially different activities that help you aggregate normalization, filtration, aggregation, classification, correlation. Correlation, for example, covers amalgamation, if you like, of several events relating to the same incident. Next stage, you'll see analysis of events, incidents, and their consequences. Prioritization is a very important function of a system like this. Decision-making, visualization. And we should certainly distinguish between automatic solutions or manual decisions. And again, automated solutions certainly can be deployed much faster, but then system can misfire. There can be false positives, for example. But then humans usually know better. They know more. They can rely on their brains. But visualization should help them a lot, because you need to help the administrator or decision maker identify the right chunks of information. In fact, this is, in my opinion, a very interesting field. I was invited to a nuclear plant in Japan. I'm sorry, I love this story. Maybe I tell it too much, but this is a great example in terms of visualization, because they have a multitude of different parameters there to visualize. So what they had essentially is this metaphor of a pasture and cows and a forest next to it, and then something changes in the system, right? The clouds covering the sun, for example. Now, it's very important to display information at multiple levels. So the decision maker does not get all the information immediately. He can be, say, reading a newspaper, drinking his coffee. He looks at the picture on the screen. It seems okay, but then first changes start creeping in. He gets a first high-level notification, and then he can drill deeper and learn more. For example, he can learn that a user has installed such and such application, and this is certainly a hole in our defense. So he can click this alert and learn about the actual change in the system configuration. Or alternatively, he learns of an ongoing attack. And if this happens, then instead of a sun, for example, he is going to see a rain or something. I think this is a great way of using toy examples to make sure that your whole audience can relate to it. But jokes aside, visualization can be extremely helpful, particularly in such a large-scale system as this one. Report and alert generation was the top-level function there in the previous slides. And here we're looking at the functional model of SIEM system. So you see that data can be either pulled or pushed. Then we have different tools we use in order to process, analyze, represent, and store information. Well, SIEM systems can actually work in non-real-time mode, but very few people are really interested in that. Well, you certainly recognize the Magic Quadrant from Gartner. This is a somewhat dated quadrant, but that doesn't really matter, because it still gives you a general picture of what's happening in this market. So you see some traditional players there. You see challengers. For example, we see HP ArcSight, IBM Q1 Labs, among the leaders shown here. Well, here they are compared on a number of different factors, number of different counts, such as real-time monitoring, data and user monitoring, deployment and support, simplicity, and so on and so forth. Importantly, you will see that they are pretty much alike. Despite all these comparisons, despite all the magic quadrants, they are quite comparable. I've given you a superficial description of SIEM systems. and the kind of requirements we have for future SIEM systems. Now, massive project. This is a 3-year program that is designed not really to develop a for-profit commercial product, but rather to develop a list of specs that will help other companies develop more than a prototype. Importantly, massive project draws upon several SIEM developers. One is SIEM. It's actually one of promising systems, although it was not shown in the Gartner report. So massive project has identified a number of limitations for the existing systems. Some of these limitations are shown in the slides, such as low scalability and so on. And there are some functional requirements for the future systems, such as proactive incident and event management, real-time countermeasure development and deployment, higher scalability, multi-layer, multi-domain security event processing. I'm going to dwell more upon some of these things in my presentation. Shown here are some of the participants of the project. A massive stands for Management of Security Information and Events in Service Infrastructure. There were 12 partner organizations. Some of them developed scenarios, such as ATAS Origin. Well, this company has been in charge of the informational processing at Olympic Games. Epsilon is in charge of some critical applications, such as a dam, for example. So ATAS is from Spain, Epsilon is from Italy. I'm sorry, Epsilon, I think, comes from South Africa. No, this must be T-Systems, because it says that they are actually an ISP, a provider. There are also a number of scientific institutions, such as Telecom Sud Paris. Polytechnica is based in Madrid. We have guys from Lisbon University, Spiras, which is my company, or rather my institute. Fraunhofer is Secure Information Systems Institute in Germany. And several developers I've mentioned are Sixcure and Alien Volt. Lots of different organizations, in fact, because we see here scenario developers, SIEM system developers, as well as members of academia. In fact, the first application here should deal with Olympic Games, another with money remittances, particularly mobile money wires, critical infrastructure management, such as dams, and this South African company called T-Systems is actually doing a lot in terms of industrial control systems. So this is the core of the system, and multi-layer event correlation is another important function. Then we have a set of different objectives related to security analysis and modeling of both attacks and countermeasure development. And again, it should all be represented differently to business and IT analysts. Alert and countermeasure generation, and also it encompasses an architecture that is resistant to failures and attacks. So the first scenario we're looking at here is the infrastructure for Olympic Games. The architecture you see there is essentially the architecture that was used in Beijing in order to support journalists, for example. So it's helped collect information on all the games. So you see a multitude of different elements there. You also see a security management center here. This is where this system is deployed, essentially. The next scenario is, well, it's pretty much an enterprise service management infrastructure. And you see a regular corporate network. So the key objectives for a scenario like this include correlation and defense. The third scenario here is called mobile money. Again, this would be a very traditional case because you need to track events, particularly anomalous events, collect information about all these events in the security management center, and react as fast as you can. And the fourth scenario deals with critical infrastructure process management, as in a DEM, for example. Because you have different levels of water, you've got a number of different sensors, you've got information infrastructure that is managing all sorts of your equipment. There are also different defense routines. So you need to provide for reliable collection of data from all these sensors. You also need to ensure reliable operation of all these devices. So you see lots of different sensors here, lots of different parameters to control. So attacks aside, we also need to do sensor management. So the idea is how we identify several different levels for information processing. Infrastructure level, data level, event level, and applied level, where most of the applications and services run. Again, this is a conceptual model. Well, you will see a number of different agents, boundary services, and hardware in the system. So in order to provide a real-time response, we need more than just a data repository. We need a data exchange bus. So its key function is to support all the mechanisms I've mentioned already, so that we can correlate, accumulate, condense, and compile the incoming information. As shown here is essentially the layout of flows in SIEM systems. So we have sensors. Next, we have the transmission group, as we call it. We have a number of information switches that collect and relay information. Essentially, this is a pre-processing, data pre-processing devices. So this is the fundamental element of the system. And there is another element that does decision-making, high-level correlation, modeling. It's also responsible for data storage and visualization. I've already described this project. I can't tell you everything about it, unfortunately, but I will focus on our area of focus. We are focusing on attack modeling and security analysis, as well as event visualization. So all these components here are outlined in red. This is a high-level design for the system. This component is called AMSAC, Analysis and Modeling of Security. So we shall talk about AMSAC, we shall also talk a little bit about repositories and decision support systems. But let's start with analytical modeling. In existing SIEM systems, this functionality, although it can be built in, is not visible. It's very important for us to analyze this information, do this modeling in order to identify potential routes of attack, potential vectors of attack, to simplify our work going forward. Secondly, it can help us correlate sequences of security events. If we can build an attack model, and if the system then tells us that there are alerts and notifies us of certain events, and we see that we are missing information on some events, it may be a breakdown in the system, or it could be a zero-day vulnerability. So we know a certain route of attack, and we see flares, if you like. We see alerts intermittently. SIEM system can provide you with more information into potential zero-day vulnerabilities. Since we have these attacker models and we are getting real-time information on what is currently happening in the system, then we can easily develop our own indicators for different levels. This is another interesting application here, because when we have different metrics, specific and aggregate ones, and then you show your administrator first the aggregate metrics, and then he can drill deeper and get an understanding of the specific ones. I hope I will be able to explore the subject in more detail. The traditional approach is that we have countermeasures per an attack. And usually you have a single countermeasure per an attack, or one countermeasure per several attacks. But we need to choose the right countermeasure, and we also want to be forward-looking, right? So if we employ AI, we probably can win some time. We can learn more about the motives of the other party. But there are some situations where we just need to bring up our defenses. Nobody can tell you for sure what the motives of the attacker are. Much really depends here on possibilities and capabilities. And using probabilistic analysis here can be quite difficult, so we end up using some hybrid tools. In fact, it's pretty difficult to ascribe probabilities to what the attacker is doing. Well, finally, we can do dynamic computation of potential impact of attacks and countermeasures on this system on defense. Well, a countermeasure, for example, can be quite good at fending off a specific attack, but it will also render, say, several internal servers unavailable, thereby undermining a critical business process. Which means that we need more than just a table which juxtaposes attacks and countermeasures. Ideally, we need a smart service that will choose countermeasures depending on their effectiveness as well as their, if you like, non-invasiveness for the business processes. This will be, in my opinion, a critical element of a future SIEM system. There have been a number of great publications in this field. They are shown, for example, in this slide. Logical approach, attack graphs that this is a very popular venue of research recently. Ontological representation has been also explored a lot recently. Evaluation of vulnerabilities, configurations, and so on and so forth. There are lots and lots of different initiatives in this field, and many of these initiatives originate in the United States. Actually, in Russia, we do have a number of projects that try to do the same, to, for example, classify all these vulnerabilities and exposures, for example. Now, another important field of research combines graphs of attack with graphs of service dependency. And it's an interesting idea to combine them. Well, in this case, you're dealing with at least two classes of graphs. One graph shows the attacks, while the other one shows service dependency. It's ultimately about trust, right? Because an attacker will go from host to host, or raising his rights, essentially, and thereby expanding his access to a range of services. For vulnerability analysis, it is very important to take into account all these aspects. Next, we're looking at representation of zero-day attacks. Well, I'm talking most about conceptual things here, but I hope they are important to the professionals. What can we do about zero-day attacks? Well, we can, for example, we won't have information on zero-day attacks, but we can have information about the weak points in configuration. We can know, for example, that certain applications are more vulnerable than the others. So for high-level modeling, we can assume that zero-day attacks can target these components in particular. Then we can look at specific routes of attack. We can develop several attack scenarios, several attack graphs. Some will be based only on existing threats, others will also include zero-day vulnerabilities. It's pretty difficult to develop this stuff manually, but actually our proposal automates the whole thing. So we've got many of these capabilities now. Now we can employ them in a number of different systems. Well, in this project we mostly rely on the SCAP protocol. There are different standards in the world of security. Everybody knows CVE, Common Configuration and Enumeration, CPE, which stands for Common Platform and Enumeration, and here again we are dealing with a standardized sets of information, different platforms. Another important standard for us is CVSS, because it gives us some, assessments, evaluations for specific vulnerabilities. So you can support, for example, security indicator calculation. There are several other very important protocols. For example, we use common attack pattern enumeration and classification. This is essentially a list or a compendium of formalized data that we can use for our own purposes. This is a list of some other protocols. CPE will, for example, tell you what kind of platforms I use. CVE will tell you vulnerabilities. CVSS for evaluations. CCE will tell you about the most secure configurations. CVE is very important in terms of preventing zero-day threats. Protocol interdependency also plays an important role in modeling, because this is the information that we can use relying on the existing configuration and the existing system events. Well, again, we are relying here on SCAP primarily, and I've mentioned some other protocols that can be used, such as TAP, EMAP, ITAP, and others. The overall approach to attack modeling, it looks like I only have about 10 minutes left in my presentation. I'm sorry about that. Okay, data storage module, which is the leftmost element in the system here, should ideally be aligned with all the standards I've mentioned. Secondly, we need to know how to properly spec the system in terms of security policies, for example, or network topology. Next, we also need to build an attack model that will represent both well-known vulnerabilities and should also allow for zero-day vulnerabilities. Next, it makes sense for us to perform a topological vulnerability analysis, which means that we not just analyze the existing vulnerabilities, but we map them across the topology of the network and the system. Also, we need to look at service dependency. We need to combine attack models with service dependency ones. Next, we get to the green element, which is attack graph analysis. Stochastic modeling plays a very important role in this respect, because we have to play with probabilities. And probabilistic analysis here is very complicated, but we can actually try using some, so to speak, boundary tools, such as what was that? Fuzziness analysis, right? Well, since we want the system to operate in nearly real-time mode, and we understand that development of an attack graph for a large system can take a long time, we should do it before the system is deployed. And then as we accumulate more events, for example, on configuration changes or events and attacks, we will be changing these graphs. It does not become fully real-time, but it is certainly a near real-time system. Some of the features of this solution include a security repository, effective methods for generation of attack graphs and service dependency. We also rely here on anytime algorithms, since we can use many models and we have a hierarchy of these models. Please note, by the way, I'm referring to theory here. We've developed some prototypes only, and for these prototypes we have limited the functionality to a certain extent. So application of anytime algorithm is important because it can provide you with information In real-time mode, if you have more time, you can employ more sophisticated algorithms, and therefore you will get a higher level of precision. And information will be updated on an ongoing basis. So the more events you accumulate, the clearer your picture is going to be. Then I've mentioned already hybrid usage of attack graphs and service dependency graphs. Calculation of a number of indicators for security, for attack potential, attack impact, attacker skills, countermeasure efficiency, and so on. The overall methodology is described here. In the preparatory stage, you develop the graph, you collect all the fundamental information, you calculate some of the key metrics. Then you actually start operating the system, you start collecting events, and therefore you start mutating, you start adapting the system. Shown here are the key flows of information. So this is the attack modeling and security analysis component, nearly a black box really. So we have here attack graphs, the weak spots. For example, a weak spot will be considered the element that is present in a larger number of attack graphs. Well, this is a very important slide because it shows how it's going to work. So we have a network model, we have our stochastic analysis. We can assign uncertainties to certain nodes in the system. And monitoring helps us correlate events and actions. So then we can extrapolate this data onto the attack graph. We also have some previous event information, and it can also predict the future for us. It can tell us where the attacker will potentially go next. Well, it's hard to be very deterministic about it, but you can give it a try. So in this slide we describe all the data we're using. And again, these are real tools we're using, and this is a conceptual tool for this component. So you see the attacker modeling module. You have also a security analysis. Shown on the right is repository and visualization modules. There are several other important modules such as correlation management module. There is also a prognostic security analyzer. And there is finally a decision support and countermeasure module. I've been very conceptual about it, but at least it shows how it operates, more or less. And Andrei Chichulin yesterday made a presentation on some of these aspects yesterday. Okay, security analysis now. You know, there have been lots of arguments about what could and could not be done, but still we need to assess the current situations and identify better ways to target vulnerabilities. So this is our topology, these are our events, and this is the attacker level and the level of the system. And finally there is the attack graph level. 5 levels shown in this slide. For example, the system level is essentially bird's eye view that tells us where we need to go next with our analysis. So we can propose a whole set of different metrics, and in fact a lot of research has been done into that. Here we go from bottom to top. Administrators usually are first shown top-level metrics, and then they drill deeper. So we identify different types of metric classes. Some are topological, for example. Others are 0 days. There could be some system characteristics. Again, these are pretty big buckets, but they are relevant for business. Actually, here we again rely on CVSS. We take the elementary readings for vulnerability assessment. I'll take 2 more minutes, okay? Topological indicators, for example. He didn't give any specific examples. Next, we're looking at attacker features say attack potential, impact, and so on and so forth. There are in fact lots and lots of indicators. We're just looking at some examples here. These are examples of indicators that are used already in modern systems. Next, we have, for example, vulnerability to zero-day attacks. For example, we have a host that contains vulnerabilities. Some of them are zero-day, and it also runs some services. It's very important for us to actually maintain the server for the business, to maintain its availability while at the same time assuring its security. So you can have this indicator of security, which will, or exposure, which will be a formula, and the actual value will range from 0 to 1, and it will depend on distance between X and F, number of vulnerabilities, and so on and so forth. Well, Meyer in 2007 proposed a very useful algorithm. He said that this exposure metrics, as well as business value, would essentially be correlated with the ease of transition from one host to another. In fact, there are so many of these indicators. I've taken the formulas away on purpose. I just gave it all as a text. Attacker skill level is another interesting subject. How would you judge the ASL? In the existing systems, you can assign ASLs to a specific step in an attack. You do realize that such an approach does not take into account such factors as, for example, random steps taken by the attacker or the attacker faking it. So ideally we need a dynamic and a more consistent approach to ASL determination. Well, I'd like to tell you more about the way we calculate integrated security indicators. Well, it starts with us calculating security indicators for different subjects and objects of the system. Then we'll look at the attack routes. For example, we have a host and we see a sequence of events. So we see several routes, for example, that target the same host, and that could be considered a whole threat. And we can have, say, a multitude of threat graphs. And this is how we actually arrive at this integrated indicator. In offline, we usually use static information, while in online, we're mostly looking at the current events. Another very interesting subject of research for us includes ontological metric-based research. So we try to correlate primary data, metrics, and countermeasures. So here we essentially describe the ontology with triplets. That's subject, predicate, and action. Oh, the last item is on visualization. In fact, so many tools are used for visualization. For example, network perimeter monitoring, user activity control. We can use pie charts, we can use histograms, graphs, trees. Some existing SIEM solutions visualize it very nicely. This is SIEM in Alien World. Here you can also get vulnerability reports and access control and distribution. What really matters to us is visualization of security events, and you can use graphs here, you can use conical circles, or you can show it all on a map. So you have your network, and here you can see the steps of the attacker. And the tree map can actually show the actual activities of the attacker. So here are some of the interfaces that we use. This, for example, is the main window. So this is essentially the top-level representation of whatever is happening in the system, and the green obviously means everything is fine. Then things happen, and the color changes, triggering the attention of the operator. Then we have system notifications. We can see some of the events highlighted. We can read vulnerability reports. We can also graphically display attack graphs, and this is the kind of representation we're using now. It can either centric, radial, or it can be tree-like. And you can also scale it geometrically or semantically. You can highlight and link if you are interested in a particular route of attack. Vulnerability reports built on tree maps can be very interesting to read. Well, this, for example, shows availability of different hosts and their vulnerability. It gives you a very quick reading of the current situation. Next, we're looking at dynamic modeling, and shown here are some of the interfaces for dynamic modeling. Here we can deal with more parameters. We can even say dynamically model delivery of packets, but I'm sorry I've taken too much time. We still have several minutes left, I think, for your questions. And if we don't have time, it doesn't look like we have enough time for a Q&A, but I'm certain that Igor will be happy to answer your questions.